Okay, so if we, in the previous video clip, we looked at just the effect of changing parameter values on the value of the option. And if I copy Black-Scholes formula and put back into the spreadsheet I have here, so home, paste, and just make this a little bit smaller, bring this one to this side here. Okay, we can see what this formula here is based on. The value of the call is based on S E negative QT ND1 minus X, where X is the exercise, E negative RT ND2. Okay. We can extend the analysis a bit here. Okay, let's just make it a little bit more visual. So I could copy. Okay, take the first worksheet out, first row out. Let's copy this worksheet. Let's go into a blank spreadsheet, a blank worksheet. So I copy everything here and paste. Okay, and we'll reduce the, just so we get everything in. And let's get rid of this graph here. Okay, so in the first instance, we were just looking at Black-Scholes, right? Black-Scholes for S, different S. For different S. Okay, so different as we increase, what we observe for a call option, as we increase the value of the underlying, the value of the call went up. So on this axis here, if we wanted to take this graph and we wanted to look at the axis, just put so the primary horizontal axis, title below axis, just S. Return. And on this axis here, so design, layout, axis title, primary vertical axis, and doesn't matter, we want to call this the value to call. Okay, so as the value of the underlying asset increases, it's clear that the value of the call, here in red, Black-Scholes, increases. Okay, what about Black-Scholes, so BS for different sigma? And again, where this analysis is going is, let's go back to our Greeks. We want some way of measuring or looking at what is the effect of changing the parameters. So if we come down to the formulas, for instance, the delta here denotes the impact of a change in the value of the underlying on the value of the call option. The vega represents the change in the value of the option for a given change in the value of the volatility. Right? So if we go back into our spreadsheet and we work out, we do the manual estimation of each of these, we could look, just visually examine the impact of changing the value of the of a particular parameter. So we could set up the following data table. In the previous data table, we just considered stock prices. We could consider this, the same range of stock prices again. Copy, home, paste, and then also consider different levels of volatility. So conceivably 10, 20, 30, and so on, maybe up to 50. Okay. Okay, and we could rerun the estimation. So let's just set out this data table here. Okay, and might be no harm to go back to the original parameter input values, and then we can examine whatever else happens. 0, 1 year. So 1045, that's a value we're familiar with. Let's run the estimation here. So what we would like to do is, considering different sigma, considering different stock or asset values, where S denotes the underlying value of the underlying asset price, we would like to rerun this value of the call for the entire range of these 5 sigmas and for the entire range of these 20 asset prices. Okay, so again, same as before, data, what if analysis, data table. On the column we have stock prices. So I go back to the original parameter input, S was equal to 100, and on the row here we have sigma, and I go back to the original parameter input for our estimation, and the table fills in. And we can duplicate the table just by setting this cell here equal to over this side, and bringing over 5 cells, and then bringing down, just dragging it down. And it's clear this, what we have here, mirrors what's the actual calculation from the data table here. Okay, now let's just graph that. What do we have? Okay, so insert and graph and hit scatter, and what we have, let's pull that down, have a look, is the Black-Scholes parameters, but for different levels of volatility. And we can see that as the volatility increases here, the value of the option increased. So for this 0.1 corresponds here, the red 0.2 corresponds with this parabola here, the 0.3 green corresponds with this parabola here, this purpley 0.4 corresponds here, and the light blue corresponds to 0.5 here. So in effect, what we've managed to illustrate is that for Black-Scholes, if you increase the volatility input, the value of the option will increase. And that's most dramatic when you're close to the exercise, or in or around. As you go deep out of the money or deep in the money, the effect of changing volatility looks very tame. But as you get close to the exercise, increasing volatility has very dramatic effects. Now, that we can do visually, and we can do it in Excel. But an advantage of using the Greeks is that you could summarize that relationship using the formula that we have here. And we'll examine these formulas in quite an amount of detail later on, but just for the moment to say, we could express what we've demonstrated here in terms of graphs and large-scale estimations. We could summarize into mathematical form, and in finance, in option theory, these mathematical forms are known as the Greeks. Okay, they're known as the Greeks. Okay, what about time? Could we do the same for time? Okay, let's have a look at this. We could copy, come into a new worksheet, just paste. Okay, as before, let's just take that down. We could say, let's just put it here. Take this cell. Okay, take this cell. Say equal to 15.05 4. Let's go back to 1 year. Original parameter inputs. 1 year, 0, and 1045. Okay. And let's consider, 0.25 years, 6 months, 9 months, 12 months, 1 month and a quarter. Okay, and then consider the usual range of stock prices up to 200. What's this? We'll call it T for the maturity, and here it's S, denoting the asset value. Let's just take our just highlight the entire range that I want to fill in. We want to generate a data table, so what data tab, what if analysis, data table, what in the original parameter inputs do I want to incorporate? Well, it's time, so I go to T here. And what in the original parameter inputs is the reference for the stock price? Well, it was this one. And it fills in, and we can insert a graph. So again, for the graph to really work well, we should set up a parallel. Okay, so a parallel matrix here, and just pull that across and pull it down, and take out the apex cell and then generate the graph. And that's as simple as insert. And again, what we observe is typically as we increase the time period, the value of the option goes up. Let's put this, the volatility of the 0.3, we get a little bit more definition, 0.4 for volatility. Now, while it is the case that always and everywhere as you increase volatility, the option price increases by some amount, that's not true for maturity. And if we increase the if we incorporate a value for the dividend yield that's higher than 0, we tend to get a tapering, right? Maybe make that a little bit higher, 0.04. In other words, what we observe is that as the volatility, as we increase the time period here, yes, when we're close to the exercise, as the maturity increases, the value of the option goes up. But after a certain point, the value of the option will actually decline. So increasing maturity normally increases the value of the option, but not always. Increasing, so this is BS for different maturities. So what we're saying, if you increase the time period or the maturity of the option, normally the value of the option goes up, but in some instances, certainly when the option is deep in the money, the value of the option actually can go down. So as we increase the time, the maturity of the instrument, sometimes, most of the time, the option increases, but sometimes the value of the option falls. Okay, now again, to get a mathematical form for that, we use theta from the Greeks. We have a neater way of summarizing this information, and the formula that we use for understanding the fact of changing the maturity is theta. Theta, however, is more about time decay, and that's something we'll have a look at later on. Okay, so I'll leave that element there, and in the videos coming up, I'll more formally introduce the Greeks.